The universe, in its boundless expanse, seems to beckon with infinite possibilities, a canvas for our grandest ambitions. Yet beneath this veneer of limitless potential lies a stark, unyielding truth. Reality itself operates under an invisible, cosmic constraint. For centuries, humanity dreamed of instant communication, of seeing the farthest stars as they truly are, in real time. We believed our vision was instantaneous, our understanding of the cosmos direct and immediate. But then, a discovery, almost accidental, revealed a fundamental boundary, an unseen wall at the very edge of our reach. This was not the triumph of a new speed record. It was the unsettling realization that the universe, our universe, had a speed limit. Consider the bustling streets of Paris in the year 1676. At the Royal Observatory, a Danish astronomer named Ole Romer was meticulously charting the heavens. He wasn't chasing the speed of light. His ambition was far more practical, yet profoundly challenging for his era, solving the longitude problem for sailors. Accurate timekeeping was key, and the eclipses of Jupiter's moon, Io, promised a celestial clock. As Io orbited Jupiter, it would periodically disappear into the giant planet's shadow and then re-emerge, events that could be timed and used to calibrate shipboard chronometers. Romer, however, noticed a perplexing cosmic anomaly. The timings of Io's eclipses were not perfectly consistent. When Earth was moving away from Jupiter in its orbit, the eclipses consistently appeared later than predicted. Conversely, when Earth was approaching Jupiter, the eclipses seemed to arrive ahead of schedule. The discrepancy could stretch for as much as 22 minutes over Earth's 6-month journey from one side of its orbit to the other, a distance of approximately 300 million kilometers. This was not a flaw in Jupiter's moon, nor a fault in Romer's careful observations. It was, Romer correctly deduced, due to the finite time it took light from Io to travel the ever-changing distance to Earth. Light, he concluded, was not instantaneous. It had a speed, and he provided the first quantitative estimate of that cosmic velocity, a figure surprisingly close to modern measurements for its time. He had, without fully grasping the immense implications, erected the first pillar of our cosmic prison. Fast forward to the 19th century, an age roaring with the engines of the Industrial Revolution. Humanity was obsessed with breaking limits. Steam trains shattered previous notions of land speed. Telegraph wires promised near-instant communication across continents. It was a time of unprecedented human ingenuity, where every barrier seemed destined to fall. Yet, the cosmic speed limit, born from Romer's astronomical observations, remained. French physicists Hippolyte Fizeau and Léon Foucault sought to confirm this heavenly deduction with earthly precision. They brought the measurement from the distant reaches of Jupiter down to their laboratories, employing ingenious contraptions of rotating cogwheels and mirrors. Fizeau, for instance, fired a beam of light through the gap between two teeth of a rapidly spinning gear, reflecting it off a mirror located nearly 8,600 meters away, and then observed if it could pass back through the next gap in the same rotating gear. The precision required was astounding. For the light to travel 16 kilometers and return through the subsequent tooth's gap, the gear had to be spinning at hundreds of rotations per second. Their terrestrial experiments confirmed Romer's pioneering work, providing an even more accurate value for the speed of light. This was not just a scientific measurement. It was a profound psychological realization. For the first time, humanity understood that information itself had a propagation delay. The light we see from the sun, journeying some 150 million kilometers, left its surface 8 minutes ago. The light from a distant star might have traveled for thousands, even millions of years, before reaching our eyes. What we see, what we know, what we experience as reality, is always, fundamentally, a delayed transmission. It meant that a cosmic traffic law existed, one that no amount of human ingenuity, no steam engine or telegraph, could apparently circumvent. The discovery of c, the speed of light, was not a moment of unbridled triumph, but a deeply unsettling revelation. The universe, in its grandeur, had imposed a speed limit, setting the stage for humanity's ultimate rebellion against this newfound, inescapable limitation. The universe, we've learned, has a speed limit. A cosmic traffic law, seemingly unbreakable, dictating that no information, no object, can travel faster than light itself. But what if this limit isn't merely a physical barrier, a speed record we're unable to shatter? What if it is something far more fundamental, an intrinsic property woven into the very fabric of existence, a law of reality itself? The true challenge is not about velocity. It is about the unbreakable chain of cause and effect. To truly grasp this profound concept, we must step into the mind of Hermann Minkowski, a German mathematician and former professor of Albert Einstein. It was in 1908 that Minkowski presented an elegant, almost poetic, geometric framework that revolutionized our understanding of space and time. He famously declared, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." This was no casual statement. It was a radical redefinition. Minkowski unified space and time into a single, four-dimensional entity known as spacetime, a continuum where events unfold. Within this spacetime, every single event, from the blink of your eye to the explosion of a distant supernova, can be charted. And for every event, there exists a unique geometric structure, often depicted as a light cone. Think of it not as a complex mathematical diagram, but as a dynamic cone of possibilities, an intuitive map of causal connections. At the very tip of this cone, at its origin, sits the event itself. Stretching upwards and downwards from this point, two cones emerge. The lower cone, reaching into the past, is your past light cone. Within its boundaries lie every single event that could have possibly influenced the event at the cone's tip. This is where all the causes reside, all the information that could have reached you before that specific moment. Every photon that struck your eye, every sound wave that vibrated your eardrum, every gravitational ripple that passed through your location, if it affected you, it came from inside or on the surface of your past light cone. It is the history that shaped your present. Conversely, the upper cone, extending into the future, represents your future light cone. Inside this region are all the events that your current actions, your present event, can possibly influence. Every message you send, every step you take, every word you speak, creates ripples that propagate outwards into this future cone. It is the realm of all possible effects, of all the realities you can shape. The very surface of these cones, both past and future, is special. It represents the path of light, the absolute, unwavering boundary of causal influence in our universe. Light, traveling at its incredible speed of nearly 300,000 kilometers per second, defines the absolute limit of how quickly information can travel and how rapidly cause can lead to effect. So, what happens if we attempt to travel faster than light? The consequences are not merely about breaking a speed record, they are about shattering the fundamental logic of our cosmos. To move beyond the light cone, to cross that sacred boundary, would mean arriving at a destination before you ever left your origin. It would mean receiving a reply to a question before you even had a chance to ask it. It would mean witnessing an effect unfold before its cause had even taken place. This is not a violation of physical speed. It is a violation of causality itself, a tearing apart of the very fabric of sequential reality. Consider a chilling thought experiment, a hypothetical device known as a tachyonic anti-telephone. Imagine a device that could send a signal, a message, into the past. Suppose you are in your laboratory and you activate this anti-telephone. You send a simple message: do not activate the anti-telephone. If the signal travels faster than light, and thus backward in time, your past self would receive this message before you activated the device. Upon receiving the warning, your past self would then choose not to activate the anti-telephone. But if you never activated it, then you never sent the message. And if the message was never sent, then your past self would have no warning and would activate the anti-telephone, sending the message. This creates an inescapable, unbearable paradox, a logical loop that unravels the very possibility of a consistent reality. The very notion of cause preceding effect, the bedrock of our understanding of existence, collapses into nonsense. This is the true tyranny of causality. The light-speed barrier is not a cosmic inconvenience. It is the cosmic bedrock. The challenge of faster-than-light travel is not about engineering a faster engine or building a more powerful rocket. It is about outrunning logic itself. It is about rewriting the most fundamental operational rules of the cosmos, a feat that would demand a universe utterly different from the one we inhabit. The universe, in its relentless enforcement of the cosmic speed limit, appears to have erected an unbreakable barrier, a wall of causality that prevents any object or information from ever reaching or exceeding the velocity of light. But what if the solution isn't to break the law, but to rewrite its very interpretation? What if we could find a cosmic cheat code, a way to navigate the vast distances between stars not by outrunning the speed of light, but by reshaping the cosmic fabric itself? This audacious concept finds its roots in the minds of theoretical physicists and, perhaps surprisingly, in the pages of science fiction. In 1994, a Mexican theoretical physicist named Miguel Alcubierre, famously inspired by the warp drive depicted in the television series Star Trek, proposed a mathematical solution to Einstein's field equations that offered a tantalizing glimpse into faster-than-light travel without actually violating the local speed limit. Alcubierre's insight was profound. Instead of the spaceship moving through space, the space itself would move around the spaceship. To grasp this radical idea, we must look to the very beginning of our universe, to an era known as cosmic inflation. Within the first fleeting fractions of a second after the Big Bang, the universe underwent an extraordinary, explosive expansion, stretching from a subatomic size to astronomical proportions at a rate far exceeding the speed of light. This isn't a violation of Einstein's relativity because it wasn't matter moving through space faster than light. It was space itself expanding. This establishes a crucial precedent. Spacetime is not a rigid, static stage upon which cosmic dramas unfold. It is a dynamic, pliable entity that can be stretched, compressed, and warped. The Alcubierre drive conceptualizes a bubble of spacetime, a localized distortion that contracts space in front of a vessel and expands it behind. The ship nestled safely inside this bubble would remain almost perfectly stationary relative to its immediate surroundings, never exceeding the speed of light within its own local pocket of space. Yet, from an external observer's perspective, this entire bubble, carrying its passenger, could appear to move at arbitrarily high speeds, effectively traversing astronomical distances in mere moments. The elegance of this solution, however, comes with an immense, almost fantastical hurdle: the need for something called exotic matter. This isn't the kind of matter you'd find on any periodic table or even in the deepest recesses of a black hole. It is hypothetical material possessing negative energy density. The concept of negative energy might sound like pure science fiction, something that exists only in the wildest imaginings of theoretical physics. It's the opposite of everything we intuitively understand about mass and energy, which are typically positive quantities. To contract space in front of the warp bubble and expand it behind, a vast amount of this negative energy is required, a quantity so immense that, in its original formulation, it was equivalent to the mass energy of entire planets or even stars. Yet, the idea of negative energy density isn't entirely without a basis in reality. Quantum mechanics, the bizarre and counterintuitive realm of the very small, offers a tantalizing hint of its existence. Consider the Casimir effect, a phenomenon first predicted by Dutch physicist Hendrik Casimir in 1948 and later experimentally verified. Place two uncharged, perfectly parallel conductive plates incredibly close together in a vacuum, separated by a distance barely larger than 1,000th of a millimeter, and a strange thing happens. They experience an attractive force. This force arises from the quantum vacuum itself, which is not truly empty, but seethes with fleeting, virtual particles, constantly popping in and out of existence. The gap between the plates restricts the wavelengths of these virtual particles, leading to a net negative pressure between them, effectively creating a tiny region of negative energy density. The force generated is minuscule, far less than the weight of a single eyelash, but it demonstrates that negative energy density is not just a mathematical fantasy, it is a real, albeit minute, physical phenomenon. This glimmer of possibility, however small, fuels the fires of exploration. Researchers like Harold Sonny White and his team at the NASA Eagle Works laboratory have embarked on highly speculative yet active research to explore the Alcubierre metric further. Their work involves attempting to re-engineer the original Alcubierre concept, seeking modifications that might drastically reduce the seemingly astronomical energy requirements needed to generate such a warp bubble. While still deeply theoretical and requiring breakthroughs in our understanding of quantum gravity, these investigations represent a shift from a mere mathematical curiosity to an area of active, albeit profoundly challenging, scientific inquiry. It means the pursuit of a cosmic cheat code, a way to bend the very fabric of reality to our will, continues to push the boundaries of what we believe is possible. What if the cosmic speed limit isn't a wall to be broken, but a landscape to be reshaped? If traversing the vast emptiness of space at the speed of light is simply too slow, perhaps the answer isn't to go through spacetime, but to go around it entirely. This is the audacious proposition of wormholes, shortcuts through the very fabric of the universe itself, bridges connecting distant points in an instant. The concept of such a cosmic bypass first emerged in the realm of pure mathematics, a curious byproduct of Albert Einstein's theory of general relativity. In 1935, Einstein, along with his colleague Nathan Rosen, discovered a theoretical solution to the field equations that described a bridge connecting two distinct regions of spacetime. This mathematical construct, now famously known as the Einstein-Rosen bridge, was initially conceived not as a method of intergalactic travel, but as a model for fundamental particles, a geometric oddity within the universe's equations. For decades, these theoretical bridges remained little more than a scientific curiosity. They were inherently unstable, snapping shut so rapidly that nothing, not even a photon of light, could possibly pass through them before they collapsed. It was as if the universe permitted the idea of a shortcut, but slammed the door shut the moment anyone considered using it. But the 1980s brought a dramatic twist to this purely academic problem. The renowned astronomer and science communicator Carl Sagan was in the midst of writing his groundbreaking science fiction novel, Contact. For his protagonist to journey across the galaxy and encounter alien intelligence, Sagan desperately needed a scientifically plausible method of faster-than-light travel, something beyond mere fantasy. He turned to his close friend, the brilliant theoretical physicist Kip Thorne of Caltech, posing a direct challenge. Could a wormhole, as described by Einstein's theory, ever be made stable enough for a human to traverse? Thorne, along with his student Mike Morris, embraced this extraordinary challenge. Their research culminated in a landmark paper published in 1988, a publication that fundamentally reshaped our understanding of theoretical interstellar travel. Thorne and Morris demonstrated that, in principle, a wormhole could indeed be made traversable and held open long enough for passage. The catch, however, was immense, echoing a requirement for another theoretical faster-than-light concept, the Alcubierre drive. To prop open the throat of the wormhole, to prevent it from collapsing into an infinitely dense singularity, an enormous quantity of exotic matter would be required. This matter would need to possess negative energy density, a bizarre and counterintuitive property that, while theoretically possible in some quantum phenomena, exists in such vast, unfathomable quantities only in the realm of speculation. Imagine needing to gather the negative energy equivalent to many times the mass of our own sun, concentrated into a tiny, stable bubble, simply to keep a cosmic doorway open. Even if such an impossible feat of engineering were achieved, the journey through a wormhole would be anything but serene. The profound physical implications for any traveler are terrifying to contemplate. As a vessel approached the entrance of a stable wormhole, the intense gravitational gradients would unleash immense tidal forces. These forces would stretch and compress the ship and everything within it with unimaginable power. pulling the traveler apart at an atomic level, a gruesome phenomenon aptly termed spaghettification. Furthermore, the exotic matter propping open the wormhole's throat would likely generate a torrent of high-energy, blue-shifted radiation. As the traveler entered, the very fabric of spacetime around them would compress the wavelengths of incoming light and particles, shifting them towards the energetic blue end of the spectrum, or even into X-rays and gamma rays. This radiation would be so powerful it would instantly fry any organic matter, reducing a human body to cinders in an instant, long before reaching the other side. And the challenges don't end there. The most disturbing implication of traversable wormholes isn't just the physical dangers, it's the profound temporal paradoxes they could unleash. Because a wormhole connects two distinct points in spacetime, and because general relativity allows for the possibility of different observers experiencing time differently, it becomes theoretically possible for a traversable wormhole to function as a time machine. Stepping through one end and emerging at the other not just in a different place, but at a different time, could reintroduce the very causality violations we thought were sidestepped by bending spacetime. Receiving a message from your future self, or worse, preventing your past self from ever embarking on the journey, would tear the fabric of logic itself, unraveling the sequential certainty of our universe. The possibility of instant travel opens the door to instant paradox. We have pushed the boundaries of our understanding, twisting spacetime to conceptualize warp drives and tearing it to conceive of wormholes, all in the audacious pursuit of conquering the cosmic speed limit. Yet, every path we have explored, from the Alcubierre drive to the Einstein-Rosen bridge, has led us back to insurmountable hurdles: the tyranny of causality, the requirement for unimaginable quantities of exotic matter, or the terrifying forces that would shred any traveler into subatomic dust. But what if our very approach to faster-than-light travel has been fundamentally misdirected? What if the true secret lies not in the colossal realm of bending gravity, but in the perplexing, almost mystical dance of the universe's tiniest constituents? To unravel this deeper mystery, we must plunge into the strange and counterintuitive world of quantum mechanics, a realm where particles can exist in multiple places at once and observation itself dictates reality. Our journey into this bizarre landscape begins in 1935 with a profound thought experiment conceived by Albert Einstein, Boris Podolsky, and Nathan Rosen, an idea that would come to be known as the EPR paradox. They were grappling with a phenomenon so unsettling, so seemingly nonsensical, that Einstein famously dubbed it spooky action at a distance. This was quantum entanglement, a property of quantum mechanics where two or more particles become intrinsically linked, no matter how vast the distance separating them. Consider a pair of electrons, born from the same event, then sent hurtling across the cosmos to opposite ends of the galaxy. These particles are entangled. If you measure a property of one electron, say its spin, and find it pointing up, you instantly know, without any further communication, that the other electron's spin, light years away, must be pointing down. This connection appears instantaneous, defying the very speed limit of light that governs our universe. The implications are mind-bending. Does information truly travel faster than light between these entangled particles? The answer, as profound as the question, is a definitive and absolute no. This is where the no communication theorem steps in, a fundamental principle of quantum mechanics that rigorously upholds causality. While the measurement of one entangled particle instantly influences the state of its partner, you cannot use this phenomenon to send a message faster than light. The reason is subtle but critical. The outcome of measuring either particle is inherently random. You can't choose the spin of the first electron to encode a message. You can only measure its random state. Since you don't control the message being sent, you cannot use this spooky action to transmit information in a controlled, faster-than-light manner. The universe, in its elegant wisdom, seems to have a built-in safeguard, ensuring that even at the quantum level, the laws of cause and effect remain inviolable, preserving the very fabric of reality from paradoxes like the tachyonic antitelephone we have previously discussed. Yet, the bizarre nature of entanglement continued to nag at the greatest minds in physics. Was there a deeper connection, something more fundamental at play? Fast forward to 2013, when an astonishing, deeply speculative idea emerged, one that forged a shocking, almost unbelievable link between the two seemingly disparate realms of faster-than-light theory, quantum mechanics, and general relativity. This was the ER equals EPR conjecture, proposed by brilliant theoretical physicists Leonard Susskind and Juan Maldacena. Their hypothesis suggests a profound duality, that every pair of entangled particles, those seemingly disconnected entities demonstrating spooky action at a distance, EPR, are in fact fundamentally connected by a microscopic, non-traversable wormhole or an Einstein-Rosen bridge, ER. This is not a physical tunnel through which spaceships could pass, nor is it a shortcut for instant travel in the conventional sense. Instead, the conjecture posits that the quantum entanglement itself is a manifestation of a deep geometric connection woven directly into the fabric of spacetime at an unimaginably small scale. It is as if the universe, in its deepest architecture, has tiny, invisible, non-passable tunnels linking every entangled pair, a web of connections operating beneath the surface of our perceived reality. Think of it not as a road you can drive on, but as a hidden fold in the cosmic map, revealing that points we thought were distant are, in some profound sense, already adjacent. The mind-bending implication of ER equals EPR is immense. What if the universe is non-local in a way we've never truly imagined? What if the shortest distance between 2 points isn't a straight line through space, or even a traversable wormhole, but an intrinsic quantum connection that exists outside of our conventional three-dimensional space and one-dimensional time? This shifts the entire discussion away from the monumental challenge of physically moving a colossal spaceship across vast interstellar distances. Instead, it invites us to consider a far more abstract realm of possibilities. In the distant future, could humanity learn to leverage these inherent quantum connections? Could we, through a deep understanding of this underlying cosmic architecture, effectively teleport information, or perhaps even consciousness, by manipulating these microscopic space-time bridges? This would represent a form of faster-than-light transfer, achieved not by breaking the light barrier or bending macroscopic space, but by exploiting a fundamental interconnectedness already present at the very heart of the quantum universe. For centuries, humanity has gazed upon the night sky, not just with wonder, but with an insatiable longing to traverse its boundless depths. We have conceived of warp drives to bend spacetime and dreamed of wormholes to tear shortcuts through the cosmos. But why this relentless obsession with breaking the speed of light, an unyielding cosmic barrier that defines our very reality? Why do we expend such immense intellectual energy, pushing the limits of physics, in pursuit of what seems, by all accounts, impossible? The answer, perhaps surprisingly, lies not solely in the realm of advanced engineering or theoretical physics, but deep within our own biological imperatives, etched into the very blueprint of our species. Consider the ancient primal drive that propelled our ancestors across continents and oceans. From the first hominids stepping out of Africa to the Polynesian navigators crossing vast, uncharted seas, to the pioneers pushing westward across new frontiers, humanity has always been defined by an insatiable urge for migration and expansion. This wasn't merely a search for resources, it was an innate, relentless push to explore, to discover what lay beyond the next horizon. This fundamental instinct, magnified by technology and imagination, now projects itself onto a cosmic scale. The desire for faster-than-light travel is not just an engineering problem. It is the ultimate expression of our species' migratory imperative, a yearning to populate the stars, to make the entire universe our home. Across our journey, we have confronted the monumental hurdles that stand in the way of this cosmic ambition. We have grappled with the unforgiving tyranny of causality, the very law that dictates cause must precede effect, a truth that faster-than-light travel threatens to shatter into unbearable paradoxes. We have faced the seemingly impossible requirement for exotic matter with its elusive negative energy density, a substance that, in the quantities needed, exists only in the most speculative corners of theoretical physics. We have peered into the violent instability that threatens to tear apart any shortcut through spacetime, whether a warp bubble or a wormhole, unleashing forces that would spaghettify any traveler. And we have stared directly into the logical inconsistencies and temporal paradoxes that could unravel reality itself if these cosmic speed limits were truly circumvented. Yet, these formidable obstacles are not definitive dead ends, signaling the end of our quest. Instead, they serve as crucial signposts, illuminating the profound gaps in our current understanding of the cosmos. Each theoretical impasse, each seemingly insurmountable challenge, points directly toward the mysteries that lie beyond our grasp, particularly the elusive quest for a unified theory of quantum gravity. This grand theory, a holy grail of modern physics, seeks to reconcile the two pillars of our cosmic comprehension, the general relativity of the very large, with the quantum mechanics of the very small. It is in these uncharted territories of physics, at the intersection of gravity and quantum phenomena, that the true answers to faster-than-light travel, if they exist at all, may ultimately reside. The profound message, therefore, is that the true value of this faster-than-light quest may not lie in the destination itself, the ability to reach a distant star in mere moments, but in the arduous, exhilarating journey of discovery it necessitates. The pursuit of faster-than-light travel forces us to confront the deepest questions about the fundamental nature of reality itself, how space-time is truly structured, what the meaning of distance genuinely entails, and what the ultimate limits of human knowledge might be. It is a relentless intellectual odyssey that pushes the boundaries of our scientific understanding, compelling us to invent new mathematics, to devise new experiments, and to challenge our most cherished assumptions about the universe. In this grand endeavor of reaching for the stars, in daring to dream beyond the confines of our immediate cosmic neighborhood, we are ultimately engaged in the most profound exploration of all, the understanding of the universe within ourselves, a reflection of our own boundless aspirations and our singular place within the vast, silent cosmos.